The second experiment in the using LT spice is VI characteristics of NMOS and PMOS devices, that is drain characteristics and transfer characteristics of NMOS as well as PMOS. So in theory I have studied the MOSFET is a 4-terminal device. The 4 terminals are gate, drain, source and body. In most of the application, body is shorted with the source, which is shown in this diagram. So body and source are shorted. So when body and source are shorted, MOSFET can be treated as only 3-terminal device, which is gate, drain and source. MOSFET can be operated in 3 regions of operation. One is cutoff region, second is triode region, another is saturation region. In cutoff region, the condition is VGS less than VT. When this value of VGS less than VT, whatever may be the value of VDS, that is drain to source voltage, the current will not flow because channel is not formed. So that is called cutoff region. The drain current is 0. Next region is triode region. For triode region, the VGS voltage should be greater than VT and VDS should be less than VGS minus VT. So that is a condition for triode region. So in the triode region, the resistance offered by the device is very small. So you can use as a closed switch in triode region. In cutoff, it can be used as an open switch because current is 0. So another region is saturation region. VGS greater than VT and VDS greater than VGS minus VT. The device enter into saturation region. So the drain characteristics, so already I studied that. So let me show it once again. The drain characteristics of a N-channel MOSFET for different values of VGS. Drain characteristics is a plot of ID versus, so y-axis is ID. So ID versus VDS. So x-axis is VDS, a DC voltage source, for different values of VGS. For different values of VGS, how the drain current varies with respect to VDS as well as VGS. So that is called drain characteristics. So another characteristics is called transfer characteristics. Transfer characteristics, transfer means output versus input. Here output is output current, input voltage is VGS. It's a plot of ID versus VGS. So when you plot ID versus VGS, the characteristics curve, the transfer characteristics will be like this. So till VGS reaches threshold voltage, the current is 0. So once the VGS becomes greater than VT, the current rises exponentially. So here we assume VDS is kept at a very high value. VDS is kept much greater than VGS minus VT, so which is kept constant. So this is called transfer characteristics. And the slope of the characteristics, transfer characteristics at particular value of VGS will give me transconductance GM. The transconductance is obtained by taking slope at a particular point. The slope is different at different points. You can see the curve is not a straight line. It is exponentially growing. The drain current is not linearly increasing. It is non-linearly varying with VGS after VT. So once it reaches VT, then it non-linearly reaches. So non-linearly increases. The slope here is different. The slope here is different. The slope here is different. So when you take a slope, so at what value of VGS you are taken the slope. So that is also important. So which means that the transconductance GM is proportional to VGS. It depends on VGS value. It is depending on the voltage VGS. Okay. So let us conduct this experiment. For this conducting the experiment, the circuit arrangement is, this is for NMOS. So I require a N MOSFET, two voltage sources, one to control VDS, another voltage to control VGS or vary VGS. So this VDD here is directly applied between drain and source. So VDD itself is VDS and VGG is applied between gate and source. So VGG itself is VGS. So these are the circuit connections. So let us do this using LT Spice, rig up the circuit, then we'll simulate this. Double click on or open the LT Spice. You create a new schematic and you save it as some file name. Save as, I'll give you some proper name for this so that later on I'll remember this. So I'll call this as drain characteristics, drain underscore CHAR of NMOS, drain characteristics of NMOS. So by looking at the file name itself, you should be able to recognize what is this file and save it in a proper directory, in your own directory. So I am saving this in my directory. So then you rig up, you take the components one by one. So go to component, take NMOS. So search in the list, you can see NMOS here, NMOS. Place it. I need two voltage sources. Go to component, take two voltage sources, place it properly. So one on the left side, another on the right side. So I need one ground. So this is ground, place it here. Then connect them using wires. Take wire and connect them. So this is connected. This voltage source is applied to gate. The second voltage source is applied to the drain. And source is common. So rig up the circuit. So according to the circuit diagram. After rigging up the circuit, create labels. So VGS and VDS. So I'll create label. So I'll call this as VGS. One label is VGS. So I'll not call it as either input or output port. So just I'll place it here. So another node here, I'll rename that as VDS. So then connect them using wire to the proper nodes. Okay, so now this region is VGS. Any point here is VGS. So any point on this line is VDS. So I have taken this point as VDS. So label is over. So next is this device characteristics I have to set. So this NMOS, the threshold voltage of this, width of this, length, and process transconductance parameter like K and dash. So all these things I have to set values. So for that you have to write a SPICE directive. Now you can see in the manual, the threshold voltage is set to 1 volts. Kp, which is K and dash, is 100 micro. U stands for micro here. 100 micro amps per volt square. W is 20 micro, that is micrometer. L is 10 micrometer. So these values I want to set. There are some more parameters like internal capacitors that will not touch now. So only these parameters I'll be changing for DC application. This is biasing or characteristic, device characteristics by applying some DC voltages across VGS and VDS. So I'll take only these 4 parameters now. For that you write the SPICE directive. So go to SPICE directive, click on this SPICE directive, and now write dot model and model name. Before this you should give some name for this model. So now see, now this is the MOSFET is NMOS. This is default name. I have to change this name. So I can give any name. I can give say N characteristics. So I'll give N underscore CHAR. So my intention is I'm using this for NMOS characteristics. So NCHAR I written. So in the manual it is CHR, something is there. So you can name this by any name other than reserve word. Now I can write the SPICE directive dot model N char. That's the name what I have given to the device. The original was NMOS, even though it is case insensitive. So I have written using caps so that you can see clearly. The original name was NMOS. Now within the bracket, you can give what are the properties you want to change. So I want to set or change the threshold voltage VTO. So VTO is equal to 1 volts. Kp, which is K and dash. K, but in the simulation you have to give it as Kp. So Kp is equal to 100 microamps per volt square. W is equal to 20 micro. U stands for micro here, and L is equal to 10 micro. So you set these values and place it somewhere on the screen. So dot model NCAT, NMOS, and these are the parameters I have set. Now what I have to do? Drain characteristics. Drain characteristics means plot of VDS versus ID for different values of VGS. So the voltages here I want to vary, or for a fixed value of VGS first. So I want to vary this VDS and see how drain current here varies. So for that what I'll do is, since I'm varying the second voltage source, I'll rename that as VDD now. The first voltage source I'll rename it as VGG, which is same as VGS actually. Now I'll move the cursor, observe this, I'll move the cursor to this V and right click on that and I'll cancel this. By doing so, what I am doing is, so I want to vary this. I'm telling that I'll write a program or I'll set some simulation setup in which VDD I'm varying. I'm not fixing this VDD. So that is the meaning. And VGG I want to give some voltage. So go to this voltage source, you'll get a hand symbol, right click and DC voltage. So let me give the DC voltage greater than VT. So VT was 1 volts. So let me give, so this voltage shows 4 volts which is greater than VT. Okay, so you can give 4 or directly or 4 volts. For a voltage source, automatically it will take units. Either you can write 4 or 4 volts. Now I want to simulate this. So I'll go to simulate, edit simulation command. So now we'll get different tabs here. So in the previous lab, I've explained this transient for when x-axis is time, AC analysis when x-axis is frequency, and DC sweep when the x-axis is a DC voltage or a current, a DC parameter. Now in the drain characteristics, x-axis is VDS, which is a DC voltage. So I have to go to DC sweep now. So now click on this tab DC sweep. You get first source, second source and third source. For the time being, don't worry about the second source and third source. Go to first source. So name of the first source, which one I'm varying. So I'm varying VDD. So write that name. VDD source I'm varying linearly I'm varying from 0 volts to approximately 10 volts. I want to vary 0 to 10, increment by 0.1. For every 0.1 volts of VDS, I want to see the simulation results. So click OK, place it here. Now we can see dot DC VDD 0 to 10 volts, increment by 0.1 volts. Now I'll save this and I'll run the simulation. So when you run the simulation, you can observe the x-axis is now a voltage, which is nothing but VDS here. So 0 to 10 volts is there. Now on the y-axis, what I want, y-axis I need drain current. So go to schematic and move close to the device. You'll get an ammeter symbol. So you can see now, you can see ammeter symbol. Or if you move away, this is voltage. Probe is voltage. I don't want voltage. I want current. So if by mistake, if you click on this, you'll get something like this, which is not correct. So you can cut this using a cutter. Right click, then move the cursor in the schematic close to this drain. You'll get ammeter symbol. Click now. Now you can see the drain characteristics. So this is the drain characteristics. Clearly you can see the device is saturated here at VDS is equal to 3 volts. So VDS is equal to VGS minus VT. So VGS was 4 volts, VG was 1 volts. So the saturation, VDS saturation is now 3 volts. That means that VDS is equal to 3 volts. The drain current is saturated. It is constant. And this is the triode region. In the triode region also there are two regions. One is when VDS is very, very small, it is almost like a straight line. But when it is bit larger, but still less than VGS minus VT, this is non-linear. Okay, so This is triode region. This is saturation region. Now you want to get family of curve. For different values of VGS, I want to see the waveform. So what to do is close the simulation. Now VGG also I want to vary. So I want to vary both VDD as well as VGG. So I want to take the second source for varying is VGG. So you remove that 4 volts now. So right click on this, move the cursor close to 4 volts, right click on that, cancel that. So it means that VGG also I want to vary. So go to simulate, edit simulation command. The first source let it be as it is. VDD I want to vary from 0 to 10 volts, increment by 0.1. And second source is VGG. So that is VGS. Second source is VGG. I want to start from 1 volts, stop at 5, increment by 1 volts. For every VGS value incremented by 1 volts from 1 to 5 volts, that is VGS is equal to 5 volts, sorry 1 volts, 2 volts, 3, 4 and 5. So I'll get a plot. So let us see now. So save the file and run it. Now move the cursor close to the drain, you'll get a ammeter symbol. Click now. Now you can see so this is for VGS is equal to 5. So this graph top one is for VGS is equal to 5 and this is for 4, this is for 3 and this is for 2, and you won't get one more curve for VGS is equal to 1 volts because for operation of the MOSFET VGS should be greater than VT. So that's why for VGS is equal to 1 volts I am not getting any curve here. So I am getting only 4 curves. So another will be in cutoff region. So for VGS is equal to 1, so I will get in cutoff region or very small current, this region. So this region is cutoff. Now at a time I want to see only one. So there are 4. I want to see only one because I want to move the cursor along this and check whether the drain currents are correct according to the theory what we have studied, the equations. If I substitute those values, can I get the same drain current or not? So to check that, I want to see only one waveform at a time. If that is the case, go to plot setting in the menu. You can see here in the plot setting, click on this plot setting and select steps. So if you select steps, so VGG, it has shown VGG for 1, 2, 3, 4, 5. So I want to see only 5. For VGG is equal to 5, I want to see. Click OK, you can see only one plot. And now you can use cursor now. And I can move along this. And this cursor you can check here. The drain current is 1.6 milliamps. This is a saturation current, which is here. So this is the saturation current from here onwards, from 4 onwards. The drain current is independent of VDS. It depends only on VGS. Because another curve will, if VGS is changed, I'll get like this. So in saturation, it depends only on VGS. So in triode region, you can move the cursor and at any value of VGS. Say let us assume here, so VGS is 5 volts and VDS is 2 volts. At this point, this is the drain current. At VGS is equal to 5 volts, VDS is equal to 2 volts. So this also you can verify using the formula. So I'll show you the manual. After completing this drain characteristics, so what you are supposed to do? So after completing this drain characteristics, simulation of drain characteristics, so what you have to do is, it is given in the manual, verify the values of drain current in saturation region using this expression. So in saturation region, we know this is the expression for drain current. Use this, and at particular value of VGS, that is in this example I shown you 5 volts, at VGS is equal to 5 volts. The saturation current, just check whether it is 1.6 milliamps. So next is in triode region, where it depends on value of VGS as well as VDS. That also I have shown, at VDS is equal to 2 volts, you are getting some current. Verify you are getting that current in triode region. So verify these equations, what you have studied in theory, derived in theory, whether it is matching with the simulation. After that, you can change values of Kp, W and L and see what is the effect of changing these parameters on the drain current and drain characteristics. So you can change this quickly in the simulation. In the schematic, you can easily change those values and you can try all these things. And also verify what is the condition for VDS for the MOSFET to operate in triode region and saturation region. So in theory, you have studied the condition for operating MOSFET operating in triode and saturation region. So whether you verify whether it is following or not. So I will show you now. Say let me show all the plots. Now you can see here, for VGS is equal to 5 volts, the current is saturating here. And for next curve, which is VGS is equal to 4 volts, the drain current is saturating at VGS minus VT. VGS is 4 volts, VT is 1 volts. So that means at 3 volts it is saturating. So here it is at 2 volts. Now the third one is, the last one is at 1 volts. So that means VDS is not fixed. VDS saturation is not fixed. It depends on what is VGS and also VT. So left of this region is triode region, right is saturation region. So that is what is given in the manual. Now drain characteristics is over. So next is transfer characteristics. So in the transfer characteristics, what you have to do is, in the transfer characteristics, it's a plot of ID versus VGS, keeping VDS constant. It's a plot of ID versus VGS, keeping VDS constant. So this is called transfer characteristics. So let us plot that. For that, I'll change in the schematic. So let me close this simulation first. I'll go to the schematic. In the schematic, I'll fix VDD. So VDD value, I'll give some 10 volts. So VDD is 10 volts, that is fixed. So VGS I want to vary. For different value of VGS, so I want to see how the drain current varies by fixing VDS. VDD is nothing but VDS here. So let us see now what is the transfer characteristics. Save this and run. Now x-axis is, so I have to change the, so I have to change the simulation command, because now VDD I am not changing. So I am changing only VGG. So first source is VGG. I am varying from 0 to 5 volts, incremented by 0.1 volts, but there is no second source. So remove the second source. So only one source I am varying only VGG from 0 to 5 volts, increment by 0.1. For every 0.1 increment of VGG, I want to plot the graph. So second source is made blank. So I don't need second source because which is fixed. So which is fixed. Now run this. Now x-axis is now VGS. Go to schematic and click. When I get ammeter symbol close to drain terminal, and this is the drain characteristics. Sorry, transfer characteristics. You can observe here. So VGS till this value is 1 volts, that is VT, drain current is 0, then it will exponentially increase. Now you can take the slope at any point here. So for that I'll show you how to take a slope. Take one cursor. So if I want to take slope at 3.5, VGS is equal to 3.5. So I'll not get slope at 3.5 directly. So what I'll do is I'll take one more cursor. So one cursor I'll keep it away from 3.5, another above 3.5, which are so these are equidistant from 3.5. So let us assume. So these two are equidistant from 3.5. And we can see now here cursor 1 x-axis value, cursor 2 x-axis value, and the difference between this is delta x and this is cursor 1 y value, cursor 2 y value, and next is the difference. And the last one you can see the slope. Directly you can get the slope by using two curves here. I can directly get the slope, which is showing 0.00043497 something like this. It is very close to 0.0005. So that means at VGS is equal to 3.5 volts, the GM value is 0.5 millimos, 0.5 millimo, because delta y by delta x, current by voltage is mho. So unit is mho. Since it is 0.00049 or close to 0.0005, it is 0.5 millimos. So this is the transconductance value. So this is how you have to conduct the experiment. You can verify. So on this transconductance varies at various points. For example, if you take around 2, so if you take the readings around 2, the transconductance value now it is 0.00019 or close to 0.0002, which is less than. Or if you take slope at higher value of VGS, so you may get more slope here, so less slope here, so moderate slope here. So that means transconductance depends on the GM, the biasing conditions. Okay. Now to label x-axis, y-axis is label is shown here. To label x-axis, what you have to do is move the cursor. Observe this. I'll move the cursor close to this x-axis. You'll get a scale symbol. Click now, and you'll get a quantity plotted. So it is showing VGG, but already I have given label for this x-axis, that is VGS as a label I have given. So I'll write this as V of VGS, V within bracket VGS. V stands for voltage, within bracket which label. So this is VGS, already I have given a label. So you can create that label now. Now you can observe the x-axis is labeled. So V of VGS, voltage at VGS. Similarly for drain characteristics also, you can give the label for x-axis. So this completes drain characteristics and transfer characteristics of N MOSFET. Here there is no design actually, so only you have to rig up the circuit, change the edit simulation settings, and plot drain characteristics and transfer characteristics, and by varying some parameters you can see what is the effect on drain as well as transfer characteristics. So next experiment is on PMOS. Similarly, you have to do same thing, you have to try for PMOS. The only thing is you have to select P MOSFET and voltage sources has to be reversed, minus and plus. Here also you can observe this is minus and plus. So only this is the difference. The procedure remains same, and the plot, if you label properly and use that label on the plot will be in the third quadrant. This plot, because drain current as well as the VDS will be negative, so you'll get plot in the third quadrant. Even the transfer characteristics also I'll get in the third quadrant. So both drain characteristics as well as transfer characteristics you will get in third quadrant. So this completes the second simulation experiment, which is VI characteristics of N MOSFET and P MOSFET.